All right, so just a few more types of problems where we can apply the fundamental theorem of calculus. And I actually want to start by applying what's known as the second fundamental theorem of calculus. And if you watch my video on the fundamental theorem of calculus, I actually led off with this. And I stated in that video, it doesn't really matter which one's called the first or the second. They're both really two parts of the same theorem. However, this is what is commonly known as the second fundamental theorem of calculus, which effectively states that the derivative of the integral is going to be exactly equal to the function that you are integrating evaluated at the upper bound x itself. So again, the derivative of our definite integral is simply going to be this function, whatever f of t is, whatever that we were integrating, evaluated at that upper bound. Now, applying the fundamental theorem of calculus, if this lower bound here, a, if this lower bound is not equal to, I should say 0, if it's not equal to 0, what you're then going to have to do is you are going to have to subtract. We're going to then find f of x minus f of c. Now, where this gets a little bit tricky when we are finding the derivative, so keep in mind in all the problems that I'm about to do right now, we are finding the derivative of this integral. And because we're finding the derivative and we're evaluating this function here at the upper bound and at the lower bound, since we're differentiating, we've just got to remember the chain rule. We've got to go ahead and find the derivative of our upper bound v and also find the derivative of our lower bound u as well. So really just keeping in mind the chain rule as we do these problems, okay? So as practice, let's use the second fundamental theorem of calculus to find, again, we're finding the derivative. We're not going to be finding the definite integrals. We're finding the derivative of these integrals at these bounds, okay? So with that in mind, let's go ahead and do this. So this problem here says, if this is my function here, let's just call this here f prime of x, if this is my derivative that I am integrating, okay? Or you know what, let me actually, just for simplicity's sake, let's just call this f of x, okay? So, and you know what, I realize x is already being used as a bound, so let's call this f of u, okay? So f of u, this is the function that we are going to be integrating, but we're trying to find the derivative of all this. And just so that we don't get lost here, I'm just going to go ahead and write that. We're finding the derivative of this integral. So what we're going to do is we're going to say f of u times our upper bound, the derivative of our upper bound, minus f evaluated at 0 times the derivative of 0. And since this is our function u, we're going to be evaluating this here at its upper bound, so we'll just rewrite this as x, f of x times x prime, minus our function f of u evaluated at 0 times 0 prime. Well, what is f of x? F of x is just simply going to be this function f of u evaluated at our upper bound. So 3x squared minus 5. Then we're going to multiply it, because we're doing the chain rule, since we're finding the derivative of all this, times x prime, which is just 1. And then we're going to subtract this from this entire integral evaluated at 0, which is just 3 times 0 squared minus 5. And you can see here, because my lower bound here is 0, and I'm finding the derivative of 0, which is just 0, we didn't really need to do all this, because I know we're going to just effectively be subtracting 0. And so this is going to be equal to 3x squared minus 5. Okay, now keep in mind, you could have also just done this. You could have also, let me just do this in a different color, and this would be the lengthier way, is to actually find the antiderivative of this function f of u, which would be t cubed minus 5t. Then I could have evaluated this integral at x, which would be x cubed minus 5x, and then subtract from it this integral evaluated at 0, which all of that is 0, and then find the derivative of all this. So basically we're finding the derivative of all this. That was the original problem. And then find the derivative of all this. And you would see that you would still get 3x squared minus 5. So this is just a way of using the second FTC to do this a little bit more efficiently. And I know it didn't seem that efficient because I kind of worked out the whole process, but if you actually just look at it, you'd see that this could have been something that you did fairly quickly once you get pretty comfortable with this. Let's try another problem. Let's do number 9 here. And what we notice about number 9 is that now our upper bound is x squared and our lower bound is x. So let's write this out. First off, we're going to evaluate this function. Again, keep in mind, we're going to be finding the derivative of this integral. We're not just finding the definite integral, we're finding the derivative of this integral. So we're going to take this function, and instead of trying to integrate it and doing all that, we're going to simply evaluate our integrand, 3t, at our upper bound, x squared. So this is 3 times x squared. And then I'm going to multiply now the derivative of our upper bound. So this is 2x. So again, this was f evaluated at v, and this was v prime. Now, let me switch colors here. I'm going to now subtract from this integrand evaluated at the lower bound, so 3 times x, times that lower bound's derivative, which is just 1. I'll put that in parentheses. So minus, this is f of u times u prime. So if we simplify all this, I'll just go to color, change the color here. So this is just going to be 6x cubed minus 3x. So that's the derivative of this definite integral. Okay, so hopefully that helps kind of understand one of the applications for the second fundamental theorem of calculus. And the last type of problem that I want to talk about in this lesson is finding the average value of the function, and specifically using the fundamental theorem of calculus to find the average value of the function. So the average value of a function is equal to the average y value that this function will attain over a closed interval where this function is continuous. So I gave you this diagram here, but I want to start with an even more basic example here. So let's suppose I gave you a function, let's just say sine x. So just sine x, for example, just kind of a basic function. Let's say f of x is equal to sine of x. And it's over the interval from 0 to, let's just something easy, pi, okay, from 0 to pi. And we know that the area underneath this curve is going to be, here in this case, a bunch of subintervals here that have the heights of sine that are equal to sine evaluated at a specific x value. Now, think for a second think about what an average actually means. The average is the sum of all values that you are adding up divided by the number of values. How many values are you actually adding up? That's essentially the idea of the average here. Now, if we apply that into the context of this problem here, well, we know that the average value of this function here is going to be effectively the sum of all these heights within, for this sine function here. It's the sum of, let me write this, the sum of all of our f of x values, f of x, the sum of all of our sine values. Let me actually move this over here so we have a little more space to work with. The sum of all these values. And then we're going to divide it by the number of f of x values that we are adding up. Well, how do we determine the number of f of x values here? Well, think about this for a moment. The number of f of x values would effectively be the total width of this interval divided by each subinterval's width, or each of these lines here, each of those widths. That's going to give us the number. This is going to give us the number of heights. Right? So if we take the total area and we divide the total width and we divide it by each of the widths, that's going to give us the number of heights here. So in the context of this problem, our total width was pi minus 0. And then we're dividing that by the width of each one of these. Each one of these have a width of dx. So what's another way of writing this? We could say, again, the total, this would lead us to being able to say something like the total sum over pi divided by dx. Another way of writing that is the sum times dx over pi, which was the total width. Think for a moment about what we just did. If we bring this all together here, we can say the following. The total sum of all the values here that we're adding with respect to x, what is that? That's effectively from 0 to pi of this function sine x dx. That's what we just found here. That's all of this. Okay? And then we divided it by pi, or the total width here, which is pi minus 0. If we put that into general form, what can we say that we just found? We found f of b minus f of a. That is to say, the fundamental theorem of calculus says that this is the area underneath this curve. This is the total area underneath this curve. minus the width of our interval, b minus a. And so if we put this into kind of a general form, we can say that the average value of the function can be simply found by taking your definite integral evaluated from a to b, which is equivalent to f of b minus f of a, and dividing it by b minus a. And so the actual formula is really simple. To find the average value of the function, or also what's known as the mean value theorem for integrals, you simply find your integral and divide it by the width of your interval, and you will get the average value of your function over the course of that interval. So let's quickly just practice one problem like this. So we can say, let's find the average value of this function, f of x is equal to x cubed minus x, on the interval from 0 to 2. So to find the average value of this function, we're going to integrate our function from 0 to 2, x cubed minus x. This is the sum of all of our heights, if you will. This is the sum of every single subinterval here. Then we are going to divide it by the width of our entire interval, which is 2 minus 0. We can do this by hand pretty easily. This is going to be 2 minus 0 is just 2, so we're going to just move that 1/2 to the outside. If we integrate this, we would get x to the 4 over 4 minus x squared over 2, and all of this evaluated from 0 to 2. I'll make that clear that it's a 0. So we can say it's 1/2. And if I evaluate this integral at 2, I should get 4. And evaluate this integral at 0, that's just 0. And so this is just 1/2 times 4, which is equal to 2. And that would be our average value of this function here. This problem also has a follow-up. It says, then find x is equal to c. Find the value of c such that the average value that we just found is actually equal to f of c. This seems pretty familiar. This is pretty similar to what we did with the mean value theorem before we talked about the mean value theorem of our integrals. That is to say, our function was x cubed minus x. We want to see what is the c value such that this is equal to 1. So we're going to say c cubed minus c is equal to 1. So we can rewrite this as c cubed minus c minus 1 is equal to 0. And this actually, you could try to factor this, but you could also just use your calculator, since that'll just save us a little bit of time. And we can see that c is approximately 1.325. Okay? So hopefully this helps break down the average value of a function, as well as how to use the second fundamental theorem of calculus to quickly find the derivatives of integrals evaluated at different bounds.